Learn how to build a stable diffusion VAE from scratch using Pytorch. VAE stands for Variational Autoencoder. It's a type of autoencoder and a neural network that trains using an unsupervised technique. They're widely used in image generation models, mainly on latent diffusion-based and GANs-based image generation models. Machine learning engineer Harsh Bhatt teaches this course.
Hey guys, in this video, we will going to learn how to implement VAE and train a VAE model. VAE is Variational Autoencoder, which has huge impact in image generation model like Stable Diffusion and DALL-E. So let's first take a look at how VAE works, and then we'll go to implement it and then train it. So to understand the VAE, we need to first understand the autoencoder, as it is the base of it. So autoencoder is an unsupervised learning neural network model. It is primarily used for dimensionality reduction. So let's suppose we want to train our stable diffusion models. We cannot feed the 4K images to train the model, which approximates to like 8 million pixels to train the neural network, which will be very computationally expensive. To solve this problem, we will need a model which actually reduces the dimensionality of this 8 million pixels into some fixed small vector with high rich features of those images. That's where the autoencoder comes into the picture, which helps us to encode the image into latents. So latent is a fixed point over the latent space. So that's it, our problem solved. But that is not, because autoencoder has some limitations when it comes to generations. So basically it is essentially designed to compress the images into latent and to reconstruct back to the original image. So it lacks the ability to generate new and varied outputs. That's where the VAE comes into the picture. Unlike autoencoder, rather than memorizing the patterns, it generates variations of images. So the major technical improvement in VAE, it does not directly generate the latents. First, it generates the probability distribution and then converts it into the latent. So by learning and predicting the probability distribution over the latent space, the VAE encodes each data points to not a fixed vector, but as a range defined by mean and variance. So let's suppose if VAE is trained on handwritten digits, so the 7 will be in one pool and the 2 will be in another pool. So every digit have a unique pools in the latent space rather than a fixed vector or fixed point. It will generate a pools of it. And then as there are pools, it has the possibility to generate the variations of it. But unlike in autoencoders where you have only a fixed vector for a specific thing and it is exactly based on what model has seen in the training examples. Suppose if we want to generate the number 7, it will going to generate the same as close to as the original one what it has seen in the training images. The VAE actually learns this by predicting and learning the probability distribution. And in the loss function, it actually uses the reconstruction loss and the KL divergence, which we're going to look at when we're going to implement this. So that's exactly what the VAE is, and I hope you understood. Let's go and implement it. Hey guys, so let's take a look at how to implement the VAE, and then we're going to train it. So I have prepared a Google Colab notebook for you, so we can I can run the code at the same time and explain you how exactly it's working. In the VAE architecture, you have this input image, the input, and then you have encoder, which basically going to predict probability distribution for you, and it will give you this two things: the standard deviation and the mean, and then you can use this to create the latent space, right? And then you can use this latent space to reconstruct back using the decoder. And then after decoding it, you have the reconstructed image. Now to train this model, you will go and do the backward pass, and the loss will be for this is reconstruction loss plus KL divergence. So reconstruction, as you already know about that, the difference between the original image and the reconstructed image, it could be like mean squared error loss. So the KL divergence basically used to estimate the difference between two probability distribution. So we add those two together and then we have the final loss, which we're going to use it to train it. And so we'll have like if we have millions of samples, we're going to train multiple times, and then it will become much better. So as this is a very large model, so you can have like millions of images, and it can able to generalize those very well. So first we have imported many modules, which is not many actually, but like some torches and math functions, sklearn to actually train testsplit, NOS definitely. So I have written some explanation for you. So let's suppose if you want to try together, I would recommend to try together, and then you can, or you can try it after and then read all the things like what exactly it is saying. I have written some notes for you. So it's a good notebook to actually have to learn about VAE, which I will gonna use too if I need in future. So make sure you have this runtime T4 GPU. So we were going to use GPU for this, and then you need to run this. I don't know why it's taking so long. Okay, it's connected. So let's go ahead, and then here we have, I have explained about the self-attention. Self-attention you might probably know. If not, it's basically give you attention scores of different tokens. If you have, let's suppose in NLP, natural language processing, if you are like have sentences, it just gives you the attention scores, which features, which tokens are more important in the sentence. So similar to in images, or basically in visual models, you have pixels. So it will give you which pixels are most important, give you the scores, attention scores. It will provide you all the KQV scores, and then you basically it has attention. Let me show you the attention score. So I think, yeah, this was very bad image. Where it is actually. What the hell? Wow. So attention is all you need. So I'm going to go to the PDF one. So attention is all you need. This will have very good information. So yeah, this is the formula. This is the formula actually which gives you the attention score, and that's what it is describing here actually. Like the lines which are dim, which has less attention scores, which are very dark, and bold, which are actually have the highest attention score. And it goes similar to pixels also, right? So here we are implementing self-attention. Self-attention are basically going to use within the same sequence. So let's suppose within the same pixels area. So they are like cross attention also, which I'm not gonna talk about here, but self-attention is basically used for specifically same sequence. So let's suppose if you have a sentence of something, let's suppose I'm Hirsch. So I'm Hirsch, it will divide into tokens of the same sequence and then match it each other. So I think it is actually in self-attention, because the law will never be perfect, and the law will never be perfect. It matching the same tokens to each other, right? So that's what self-attention is. So it goes against the same idea with the images. So you have, let's suppose you have to imagine they're like pixels, and then the same pixel will be here, and then it will match and have a score of with each other, right? So that's so in init function we have self-dot number of heads, as we are like doing the same process of. So in the init function we have number of heads. In projection layer, which is a linear layer, which goes with dimension of like embedding dimension, and 3 times of embedding dimension, as we want to actually divide it into 3 tensors, which is like QKV. You might already know about it, so I would recommend to read this paper to understand about the self-attention. It has like because it these three things which help us to attain the attention score, Q, K, and V, right? And this thing in the root, it is the constant. So now it's, if you want, bias is equals to in projection bias, it's like true here, and then out projection is the output of this self-attention, is the embedding dimension and embedding dimension, and the bias will be based on the argument, right? So, and then we have self dot d heads, which is like dimension of heads. So the dimension of heads will be like the embedding dimension divided by the number of heads we have. And the forward metal will have like this thing. The X will be like a batch size, sequence length, dimension. The batch size is something we will have. The sequence length in the images and images terms, it will going to be the multiplication of the height and width. So the, let's suppose if we have 3 by 5 images, the 3 by 15. So 15 it will be the sequence length, and dimension will be the number of channels of the images here. So we are just extracting from this X the shapes, and then we are defining interim shape, which is the required shape we need to do to calculate the attention score in parallelly, which is the batch size, sequence length, and we are dividing to number of heads and the dimension of heads. And then here we are getting we are calling the in projection layer, and then we are chunking it out into 3 different tensors, which has a shape of batch size, sequence length, and D embedding, which is dimension embedding. And then we are changing it to the interim shape, that is the required shape to do the to calculate the attention in parallel. And then we are like transposing it to attain this shape, which is this one. Earlier we had this sequence length, number of heads. Just we are like transposing it to just swap it out, swap this thing. Head number of heads will come earlier and the sequence length will come later, right? Yeah, so basically the batch size, number of heads, and the sequence length, which is the heights and widths, the multiplication of height and width, and the number of channels you will have. Okay, so now after that we can calculate the attention. To calculate the attention, we have weight, like the first part, we are calculating the first part, which is like Q matrix multiply by K dot transpose. We're transposing it to actually to have the right shape for the matrix multiplication. So after that, if you want to fill mask in the weights, then this code will actually do that, and weights dot mask will fill the mask. And then we have the weight divided by, so it's the same formula which we have seen it here, divided by dk, right? This is the same. And then we are doing the f dot softmax function. So here we have the softmax, and then the last we will multiply it with, here we are multiplying it v, and then transposing it back to the original one, interim shape, sequence length, number of heads, dimension divided by heads, and then change back to the what it is required to have the output projection. This is batch size, sequence length, D embedding, which was equals to what it has been during how it came actually here. And then we are using calling the out projection to get the output. So that this is the all self attention, and the attention block is basically, so this is all about the self attention. And then we have the attention block, which just uses this self attention in the residual VAE. So basically, you probably know about the residual. We need to use the residual layers here because residual layers allow us to do the skip connection, which help us to create a deep network. So if you don't have residual layer, or if you don't do the skip connections, there's a probability, like not probability, but yeah, definitely the model going to be overfit with few layers. And we possibly can't train the very deep large models with large parameters. So the large data will not able to generalize that well. So this attention block, so this initializes first group norm and the attention, which is a self-attention module, which we have defined. And then forward, we have this residual, which we are loading the X first, and then calling the group norm, and then we are changing the shape to actually work with attention, self-attention module here. And then, so basically, as I described, we need batch size and then the sequence length and the channel. So as in the input, we have batch size, channels, and H and W either width. So we are just getting the features H multiplied by W. So here, I think here we're doing it. So we are changing the shape here. X dot view would be like H multiplied by W. So we will have just number of batch channels and H and W, which is the features here. And then we are transposing it. So the H and W will become here and the channels. So when we have the output from the attention, we can just transpose it back, and then in the last we are just adding the residual here, which should be residuary here. Yeah, okay. So this was this attention block, and then we can, like, I think I've called this one not okay. Yeah, and then I have to call this. And then we have residual block specifically for encoder and decoder. So here I'm initializing the group norm, so normalization layer, and then con1. So in residual layer, we don't actually change the shapes of the input. So here also, like, we haven't changed the shapes in attention layer, like the shapes were the same, and also the output was the same, output shape was the same. So in residual layer, the input and output shape will be the same also. So the con1 will actually extract the features, but it will not change or reduce dimension as, because the kernel size will be 3 and the padding 1. When the kernel size is 3 and the padding is 1, it don't change the shape. I think there is a formula for that. You possibly can search it out. To when you apply con2D, there's a formula that based on in channels and out channels, how much the it reduces, how much the shape is going to reduce, or the height and width going to be reduced. So this will not change the shape, neither this one. So there are two blocks here, like the first is the group norm and con1, and group norm 2 and con2, right? And if there's an in channels, out channels are same, just define the another identity as residual layer, right? So in forward function, we have batch size, in channels, and H and W, and then we will just using the residue here, x.clone, and then calling the group norm, and then there's a like activation function we are calling, and the con1, and then the second block, which is the group norm 2 and the con2, and then at the end we are adding the residual layer and x, right? So then we are moving forward to the encoder. So encoder is more interesting as it has more layers, and like it's going to actually do the main work for us to convert into latents. So this whole class is basically sequential layer. So directly defining this in our super.init, and So first we have this con 2D to actually, so basically the intention for it is going to be here. So we will basically reduce the dimensions from here. So you're going to see a lot of con 2D layers. And so the first we have the con 2D layers, which actually I've also defined here the shapes, like the what was the initial shape and how it's going to impact, and like what exactly the output shape going to be. So here we're not changing the size of the image, but just the channels. And then we have residual block. So we were going to use more various, so we were going to use a lot of residual block in between, because we need to have a very deep network. So we were going to use residual block a lot here between the con 2D. So then we have another con 2D, and then here we have stride 2, so which has h divided by 2 divided by 2, so half the size of the image now we have. And again residual block, and con 2D, now we have the divided by 4 size, and then we have residual block. So it's kind of same pattern you have till we do this until here, until we reach the h divided by 8, like until we reach h divided by 8, w divided by 8, and then we can just use the attention block here for doing the attention stuff. And then again we in the end we have just we can use residual block, and then in the end block of it we are using residual block and group normalization, and this CLU function activation functions, and this con 2D layers. So the final shape will be going to be batch size 8 channels, h divided by 8, w divided by 8. So we have reduced the size of the image very much, and then we can use it to generate the latents and then decode it back. In our forward function, first we are doing is we are padding it. So x equals to f dot pad, so it's going to pad it to the right and bottom, and then after that we are chunking it the mean and variance, which is the most important part of the VAE. Initial size we had batch size 8, h divided by 8, w divided by 8, and then we are generating the not generating but like chunking it into 2 tensors, which is batch size, and then we have like 4 dimensions, because we are just chunking it in dimension 1. So this is going to be half, the channel is going to be half, so yeah, from 8 to 4, and this will going to be the same. So mean and log will have the same inner dimensions, which is like h divided by 8 and w divided by 8, and then we are doing is we are doing log. So this is the log variance, so it's not the variance, log variance, which we're going to use to clamp. And then we are doing the reparameterization technique, which is the process of generating the latent. So how we're doing is, this is the STD, standard deviation. So we can use the log variance and then call this torch.exponent function to have to generate the standard deviation. And then this EPS is basically the EPS is something, I think, wait, what is EPS? Yeah, I think EPS is basically the so EPS is so EPS is the constant, so it's like torch or trend line, and then so this is the formula for the generating the latent. So the x is our latent, which we can also say it like a z, and then we are just multiplying with some constant, which this constant is coming from like a diffusion library, and in the decoder we will going to divide it also, this constant. So this was all about the encoder, and now let's take a look at decoder. So in decoder, we have again this, so the intention, let's take a look at what are the intentions. So now we have the latent space. The intention to use the decoder is to actually use this latent space to reconstruct back the original image. That's what the decoder is going to do. So again, it's a sequential layer. It's going to it has various residual layers and contour layers. The main layer in here is upsample. So nn.upsample, which is going to upsample by a factor. So here it was earlier we had like batch size for 32 by 32 image, and then when we're going to call this function, it's going to upsample it by a factor of 2 because the scale factor is 2, so it's going to be 64, and then we are calling it at a certain interval after defining continuity and a social block, and then here we the same scale factor, which is 2. We have 128, and then we're going to do this again to by 256 because our input image is going to be 256 and output image is going to be 256. So, and then we actually again using the group norm and then nn.sedu activation function. In forward method, first we are actually removing the constant what we have multiplied it with x, and then we just like iterating it all the modules we have in the decoder, and we are returning this x, which is the output. So the output will be going to be, the shape will be going to batch size, 3 will be the channel, so the original image in channel, and the original image height, original image width. We are going to return it. So that was the decoder, and then we can call it, I think I haven't called this encoder yet, call this one also. Encoder and decoder. So yeah, so this was all about the VA, and now we can like use these modules to actually train the VA. So the next part is to download and process data. So I already have this data set of dogs. It consists of images of dogs of various breeds, and then you have this, you can unzip it, and then here this function we're going to split it into the training and test dir, and this class, this is the last module which wraps all the encoder and decoder. So we can call this, and then the last cell we have is, and then we have like a train VA. So here we are basically using this VA module to actually to create a training loop, and then to do the back forward and backward pass. So let's take a look at what are the constants and how we are defining it. So the number of people are going to be 100, just like you can tweak it up like to certain level and how much you can train. Learning rate is like 1e. This is, so learning rate is like a typical learning rate for VA, which I think probably it can converge it better with that, but you can tweak it if you want to. And then we have beta, which is like KL divergence weight. So as I mentioned, KL divergence is used to find a difference or calculate for the comparison of two probability distribution. So here we will use this in the KL divergence loss. This will transform to a specific shape. The transforms.compose function. Batch size will have 4. You can just tweak it up based on your memory uses. And data set, this defines data sets, and then it's a data loader. We are defining data loader from here. And then here we have a model using the VA module, and then the optimizer will going to be the Adam one. Yeah, and then here we have learning rate. Also we are like using accumulation of step. So we have here, wait, I think, yeah, we are just using accumulation of steps. If you don't know about the accumulation of steps, I would recommend to a little bit read about it, like how this works. Accumulation of steps, it's basically like normalize the loss to account for accumulation. So although like the, and here just we are storing the training losses. So in our training, this is our training loop. Now we can train our VAE now, finally. Okay, so just model the train typical thing, and then here we are iterating over the data loader image, putting into a device. I think device we have, what was, yeah, CUDA it was. So, and then forward pass, it will return the constructor encoded model. So as the model was VAE, which returns the two things, decoded and encoded, right? So reconstructed, which is like a decoded and encoded the latent vector, and now we need to compute the loss. The reconstruction loss is going to be MSE loss, which is going to be reconstructed and based compares it with images, the original image. Then extract mean and log variance from the encoded. So as we have already mentioned it, so we had the latent, so now we are again extracting it, mean and log variance. Although like I think you can try it up with not again splitting up like in. So I think here I'm like first chunking it into mean and log and then defining it again. I think that's the right way to do it, I believe. And then again I'm extracting the mean and log variance. But let me know if you read or like know that we can do any other way. Based on what I know, we can extract again mean and log variance and then use it over the KL divergence loss to calculate the KL divergence. So this formula calculates the KL divergence. I think you can read more about the KL divergence already. Formula. So this is the formula actually. So you can read more about it possibly. So this KL divergence, we will going to use it as it was mentioned here, reconstruction plus KL divergence. So the total loss will be equals to reconstruction plus the KL divergence. So we are like multiplying with a constant. The KL divergence, we're going to have a constant multiplied, which we have to find here, the beta. Now we have a loss, and then now we can do the backward pass here, and this to the optimizer.0grad.step, optimizer.step and 0grad, and storing the train loss and stuff. This basically I wanted to see like reconstructed image, so at every step I'm like generating this reconstructed image, reconstructed.py, which you can actually try it out during the training. You can just at every step it will save the image, so you can check it out like how exactly the reconstructed image look like. So I think let's call this and let's see how exactly this is training, and then we can check it out, the constructor.py png. Yep, so it started training, and yeah, and then this is the reconstructor.png. Looks like a very small image, but I think, yeah, initially you probably won't be able to see anything, but after like training at a certain level, you possibly can see the dog images here. So that was all about the VAE, the implementation, and how to train it. Hey guys, so this is a second part of the video of building and training VAE. In that video, I explained how to build a VAE from scratch and how to create a training pipeline of it and train it. So in this video, I have trained a VAE till 19th epoch. So this is my trained model file. What I'm gonna do with this is I will gonna use our custom VAE, like the VAE we have implemented here, like this VAE, the model we have implemented, all the things, encoder and decoder and attention block and decision block. We will going to integrate this into the stable diffusion pipeline, and then we will try to generate an image with that. That's why I have trained this VAE till 19th epoch, which is still very early and still not very generalized, but it's gonna work in the way where we can just recognize whatever we are prompting. So let's try this class VAE. So this is our older VAE section, but for that, making compatible with diffuser library and diffuser stable diffusion pipeline, to create our custom VAE, which has some specific functions. So this is a custom VAE, and then this encode function, this decode function, and the forward function will just only return the X reconstructed. Z is the latent from the encoder, and the X reconstructed is the image we have from the decoder. This load pre-trained weights will going to load the state dict, this model which we're gonna use. And then we have another module, which is a diffuser compatible VAE. Here we are loading autoencoder KL, which is like another module, Pytorch module, which help us to create compatible VAEs with like diffuser compatible VAE. So I'm using here as an inheritance. So this diffuser compatible, we have all the functionality what autoencoder KL has. Here I'm just defining self.va to VAE and getting the VAE from the constructor, and then the encode and decode function. Here are some of the things I'm printing just to like debug and stuff like that. So yeah, I think just run this thing and then run this thing, and then here I'm loading the this comp vist / stable diffusion. You can just I can go here and show you what kind of model this is. This is a stable diffusion model. Yep. Oh, it was released on I think 2022, and yeah, I think this model will work with our VAE. It is a 512 by 512 model. By running this, you can download this in the local dir here, /model dir, and then the next you have to do is like you have to just check it out, like what exactly the VAE structure of it, and I have basically tried to look at it. Okay, what are the things it has, and what are the things I need to be made compatible, like whatever the VAE we have constructed, implemented, how to make compatible with that autoencoder KL VAE. So the next we have is like I'm just importing a torch. Here I'm loading our trained custom VAE, which is like here VAE model epoch 90.pth file. This is a pth file. Map location is CPU. So in this section, I am replacing some typos and stuff. So because like there was some missing keys and stuff like that. So and it was not very compatible. Like our implementation was not compatible to the what we wanted to actually do with stable diffusion. So I have to actually replace some namings and stuff. All the way, like the architecture is same, but the namings and stuff is different. That's why I'm using this. so this code will actually replace some names and stuff, but the architecture going to be the same, and it will add all the keys and stuff there, right? So this is what it does, and then it just loads the VA. Then we can just see the architecture of the VA here, and you can just check it out, like how it is constructed, and match it out like the other VAs, or basically you can load other VAs, like I'm loading this one right now. This a diffusion model. You can try to load another diffusion model, possibly like it should be like 512 by 512. Because if you go with SDXL, something different, bigger models, it won't work. So yep. And then what we are doing is, like, we are just loading the stable diffusion pipeline, this VAE, custom VAE, compatible VAE, and then inside this we are just putting the VAE. And then here, stable diffusion pipeline dot from pre-trained, the stable diffusion model, and here we have the option to integrate the custom VAE or whatever the VAE you want to integrate. So this is, here we are just injecting the compatible VAE, and then the pipe.to and moving to CUDA. Let's run this. And here prompt is a photo of a dog, and then we are running the pipeline with inference step is 50. So let's see how this image will look like. I'm using this from a photo of a dog because our VA is trained on the dog photos. So let's see. Okay, so it does look like a dog, like you can just recognize it, although like the image quality is like very noisy because the VA is trained till only 19 epoch. It should like go to like 100 epoch or something like that, and like originally VA is trained till like a huge number of hours. So we haven't trained that much. I don't have that much compute at the moment to actually train that, but if you want to try, please try it, and then try to integrate that VA, and then try to see how the image quality is improving, and let me know, guys, how this will work if you want to try this out. But that's it for this tutorial. I hope you enjoyed and understood. Let me know if you have a question, and if you want to see more content like this tutorials, subscribe to Coded Hirsch. Thank you guys for watching this video. See ya.